And this leads to a significant amount of redundancy pixel processing, as redundancy information between the frames is repeatedly interrupted. And this is the frame level redundancies, which is a significant amount of redundant pixel processing. So by analyzing the involvement distributions of all iteration, and we see each iteration, we observe that inter-iteration similarity in the workload distribution and intra-iteration workload imbalance. At the iteration level, there is this intra-iteration redundancy flow assignment across the pixels. And we first need to introduce the sub-level pipeline before presenting our providing result on the sub-level. In each step of 3D Gaussian state tracking and mapping, there are 5 states, both of them. The first is preprocessing, which projects the 3D Gaussian onto the 2D image pipeline. Based on the Gaussian distribution, the scene is divided into tiles. And the second step is sorting, where Gaussians in each tile are sorted according to their depths. And the third step is the rendering, where the colors of Gaussians covering each pixel are computing and are blending from near to far to generate the final pixel color distribution. And the first step is the rendering propagation, which backpropagates the color gradients to each 2D Gaussians from the color loss. And the fifth step is the preprocessing propagation. During mapping the 2D Gaussian, pass their gradients back to the corresponding 3D Gaussians. And during the tracking, the process goes one step further, propagating the gradients from the 2D Gaussians to their counterparts. And according to our final results, in both tracking and mapping, the rendering propagation dominates the 3D Gaussian scenes pipeline, accounting for more than 80% of the total execution time. And during the propagation, the gradients of affected pixels are automatically aggregated to ensure the correct gradients accumulate across overlapping the Gaussians. So the result in massive time consuming atomic add and operation in propagations. For example, during repetition, our gradients computation takes about 20 seconds, while other operations take only 8 seconds. This also leads to imbalanced pipeline during the rendering and the rendering application. So we calculate the influence of each Gaussian gradients on the final camera gradients. As shown in the figure, about 86% of Gaussian in rendering and rendering application are less important. So there are massive number of rendering redundant Gaussians are involved in computing rendering and rendering propagation. Yet they have only a minor impact on their final camera optimization. So these are 3-step redundancy we can observe at the step level. This multi-level redundancy must be addressed. A potential solution is to leverage the existing 3D Gaussian scaling pipeline to efficiently manage the overhead of environment and reducing this redundancy. This allows us to eliminate the redundancy without introducing additional overhead. So at the obvious level, to address frame level redundancy pixel processing, we introduced dynamic downsampling, a method that dynamically reduces the resolution for non-T-frame. To tackle step-level redundancy Gaussian computing, we propose adaptive pruning, which combines gradient-based importance evaluation with the mask pruning strategy. So the downsampling reduces the resolution of the non-K-frame by leveraging two key observations. The keyframe are more important than the non-K-frame, and the consecutive non-K-frame escape high scenario. We use the originally resolution for keyframe and apply progressive downsampling to the non-K-frame. And with this way, we tackle the first frame level redundancy. So this is the redundant processing. And to address each feature of redundant Gaussian, we propose adaptive pruning, which performs pruning based on the existing gradients to avoid introduce additional overhead. To enable skipping, sorting, and intersection, we introduce a masked pruning strategy, which masks the Gaussian in every iteration and pruning in every case iterations, which allow the system to reuse the Gaussian distribution from the previous iterations, and thereby skip redundancy, sorting, and intersection operations. So use this tool, through this two methods, we address both frame level redundancy, pixel processing, and step level redundant Gaussian computing. In hardware design, we propose three techniques to address different bottlenecks, which is iteration level redundant workload assignment, step level capital invariance, and step level time consuming operations. So we propose RTGS plug-in accelerator design to speed up rendering replication and pre-processing replication in the 3D Gaussian stream. RTGS include specialized compute units RE for rendering and replication, and PE for pre-processing replication. It's supported by global Gaussian CAD, which is 80 kilobytes, and Gaussian merging units that use tree-based merging function. The Gaussian merging units use tree-based merging function to handle the challenges that traditionally other trees are designed for dense aggregation, whereas the 3D Gaussian system requires efficient sparse aggregation, achieves through detected GMU hardware with bypassing. We address that level of time-consuming and cutting-edge operations through the design of the GMU. Since we analyzed before the rendering and relocation domain the 3D Gaussian system pipeline, our main contribution focuses on the REs, incorporates local scattering units for parallel scattering and R&D buffer to efficient current release. The local scattering units, which I call WSU, performs parallel local scattering between the light and heavy pixels due to their highly symmetrical distribution. To overcome this challenge of scattering and associated overhead in each iteration, we introduced a pixel tiling configuration table in the WSU to reuse the inter-iteration scattering information. Okay. And R&D buffer is designed for current reuse. The challenge is that a simple reuse color gradient from the R&D buffer during the rendering and replication still causes pipeline imbalance. For example, it's changing from 80 to 20 to 8 cycles to 4 to 8 cycles. Our solution is to reuse and reallocate the default threshold balance pipeline. And we address the remaining three types of redundancies through the three hardware design, which should distribute above. So the local times. Lower is to under 10 gigabytes, which the 8 gigabytes requirement, while still achieving the SOTA performance in the training APIs and PSNL. Okay, this is the whole piece of my presentation, and thank you all for your attention, and I'm very happy to take any questions.
Any questions, please, from the microphone.
This work is streaming through the Gaussian, based application through the Gaussian. So I have a question of your second part of your slides, which shows the time the forward and backward part, the BP. The BP time is less than the render time. And I have calculated the training of the outside and find the forward time is maybe less than the backward time. So what's the difference? Why the BP time is low in this application?
I think in this figure,
No, it's pretty
so the question is whether it's the training time is larger than the user time of the silicon.
So it's larger, right?
Yeah, the training time actually is larger than the inference.
Oh, I thought it is. So
I think in this thing, maybe the training time is larger than the 3GF training, because it involves some at point. If we processing the key frame, we will process some area we never seen before, so we need to add the Gaussian. So it will take a long time, because it will include the initial part of the Gaussian, like the Gaussian part and the Gaussian training part. So the two are combined together. So the training in the silicon stage should be larger than training in the silicon.
do we have a distribution of different part time in your slides?
I think it's in this figure. Yeah, I think the form is the random multiplication time. 3 is in the random, so the calculation time should be larger than the random time. Okay.
Any other questions? Is there a microphone? Okay, I had a question about the atomics, the heavy use of atomics in the baseline. And then you mentioned you construct this tree. So is there runtime overhead in the solution for the
Yeah.
Gaussian?
If I try to tackle the upcoming overhead, the new tree will bring like new overhead system communication, but because there are lots of optimiers in this system, because one Gaussian will cover a lot of pixels, and there are a lot of Gaussian in as well. So I think the overhead of the other tree is good enough compared with the original optimier.
Thank you. Okay, if there are no other questions, let's thank the speaker again.